Good morning, afternoon, slash night, slash 2 a.m. pre-calculus, depending on when you're watching this. I do know there's one of you out there watching it at 2 a.m., even though you're never supposed to do math after 9 p.m., that is. Never do math after 9 p.m. Why? Well, because sleep is a thing. And if you don't sleep, how are you going to do your pre-cals? Today is a very important day for us. The topic is rational functions, and I say it's important because this is going to be, in a kind of a general way, this is going to be right where calculus picks up. All right? So, first off, rational functions. A rational function is when you've got a fraction. Remember, rational, the root word is ratio, which ratio means function. Or function, wow, fraction. So px and qx are polynomials. So a rational function is when you've got a polynomial in the denominator. All right? Now, p of x can be just a single term. It can be a constant, but the basis here is that your x values are going to be in the denominator here. So the parent function for a rational, this guy right here, you get this up and out of the way here. So we've got 1 over x is the rational parent function. And let's just put a few numbers in here and see what happens. So let's say we go from -3 to +3. And if you put these values in here, you'll get a -1/3, -1/2, -1, 0, or excuse me, plug a 0 in for x here, and we get 1 over 0, which is undefined. Interesting. Let me zoom in on this portion here. Plug in a 1 and you get 1. Plug in a 2, you get a half. Plug in a 3, you get a third. Okay, so we start off with -3, comma, -1/3. We go to -2, -1/2, -1, -1. 0 is undefined. And then it pops up to 1, 1. 2, comma, half, 3, comma, third. And if it was a 4, it'd be a fourth, on and on and on and on and on. And at 0, you get this weird kind of thing that happens. It becomes undefined. Well, to get an idea of what's happening right around 0, what happens if you put a 1/2 in? If you were to put a 1/2, 1 over 1/2, you'd have to multiply by 2, and you'd end up with 2, right? So 1/2 is 2. -1/2 would be -2. So what this thing is doing then is getting really, really close to the y-axis, but not actually hitting it. And then it's going to get really, really close to the x-axis, but not actually hit that. Imagine if you put go out to where x is 100, 1 over 100. Well, it's still positive, and it's really close to 0, just not quite there yet. And same thing with this one. Out like this. Okay. So let's answer some questions about this, because there's going to be some where we have to go through and answer a few questions. First, what is the domain? Let me zoom out so you can get a picture of the graph here as well. So the domain is all the x values. Well, the only x value that is no good for us is 0, because that's your horizontal asymptote. So I'm just going to say, to make it more simple, is x cannot equal 0. That's another way of saying it goes from -infinity to 0 but doesn't touch, and then goes from 0 to infinity but doesn't touch, right? Your range is actually the same thing. Y can be everything except 0. Y cannot be 0. Then we've got VA and HA. Now VA is a vertical asymptote. You did learn about these in Algebra 2, so this is just going to be a review. Vertical asymptotes are a vertical line where you cannot touch. In this case, they're measured with X, so we've got a vertical line where we can't touch. All over here, the only place that we can't touch is going to be 0. So my vertical asymptote is X equals 0. So a way that you can kind of think about that, an asymptote being a line you can't touch, let me do this in like that there. Well, can't really see that, can you? So there's your vertical asymptote. It's a line that you cannot touch vertically. And then on the same note, you've got a horizontal asymptote, which is a line that you cannot touch horizontally. And that's going to be measured with your y values. Y equals 0. Alright, so again, this is something that you did do in Algebra 2. If you don't remember it, that's fine. This is just a little bit of review for you. Symmetry. Even, odd, or neither. Right? That's what this is coming up against. So it looks to me like we have an origin symmetry. Alright, origin symmetry means that this is going to be an odd function. Remember, origin symmetry is the y value, x and y values, like the point 1, comma 1. Put a negative in front of both, -1, -1, and you're back on your graph. Is it 1 to 1? So does it pass the horizontal line test? It sure does. Is it increasing? Now this is actually where people are going to have to focus. Increasing. Where is this thing increasing at? Well, remember, we always read a graph from left to right, right? If we always read a graph from left to right, let's start over here, and it's decreasing, right? It's going downhill. Decreasing, 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 asymptote. Decreasing, 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 decreasing. This function is continuously decreasing. There are no portions of this graph that are increasing. Pretty cool, huh? No portion of this graph is increasing. Now, what that means for us going forward in the future is that since it's all decreasing, if you were to throw a negative in front of this thing, then it'd be all increasing. That kind of thing, which you'll see in just a second. So, everything is decreasing. You're decreasing from negative infinity to 0, and from 0 to infinity. And I've heard a lot of people say, well, you can't go from negative infinity to positive infinity without increasing somewhere. But that's not the point of what's happening here. Because of the vertical asymptote, because it goes from decreasing to decreasing, because of this vertical asymptote, we don't have to include 0. So I've heard a lot of people say, well, wouldn't it be increasing at 0? No, it won't increase at 0. That's an asymptote. Is there ever a place where it's constant? No. Discontinuities. Is there any place where the graph breaks and jumps from one value to another? Well, yeah, right at 0. It goes from negative infinity to positive infinity. So is there a discontinuity? Yeah, x equals 0. That's a discontinuity. Discontinuous is what that means, meaning not continuous. Continuous is something that happens if you put your pencil on the paper and you draw a graph. If you ever have to pick your pencil up, like right here, I have to pick my pencil up, bring it up here, and then finish the graph, then it's discontinuous at that point. All right? This function is also called the reciprocal function. Do you see why? The reciprocal function. Reciprocating meaning a reciprocal is when you flip a fraction. Like if you have the fraction 2 over 1, which you know is just the number 2, and you flip it, you get 1/2. 2, 1/2. So see, there's a little bit of order to this madness here. All right. Graph the following transformations of 1 over x. Now these are much more simple than you would think. All I have to remember is that when you modify x, it's going to move left or right. When you modify anything outside of this fraction, it's going to go up or down. You can multiply it, divide it, all that jazz. So for this one, the big thing about these are picking out your asymptotes, right? So we're going right 4 and down 5. Excuse me, left 4 and down 5. So originally my asymptotes were the x-axis and the y-axis, right? But now, from 0, 0, I'm going left 4 and down 5. Let me do this with a different thing here. So this can kind of show up on the video a little bit better. So I went left 4 and down 5. And then the points I want you to remember are 1, 1, up 1 over 1, and down 1, left 1. And then from there you can kind of rough sketch it. So those are the points I want you to remember. The up 1 over 1, down 1, left 1. Let me zoom in here so you can get a better picture of it. Alright, so your domain, again, is x can equal everything except the asymptote of -4. Your range is y can equal everything except the -5, the horizontal asymptote here. So your vertical asymptote is x equals 4. Your horizontal asymptote is y equals -4, excuse me. See how those two kind of correlate? Okay. Now if you notice, the vertical asymptote is probably the easiest one to find. It's just where your denominator equals 0. Right? So over here, remember this is a negative value and it's moving up 2, or yeah, moving up 2. So let me rewrite this here as -1 over x minus 3 plus 2. So I'm going right 3 and up 2. Right 3, up 2, there's my asymptotes. And originally, it would have been up here, right? Up 1 over 1. But now I have this negative out here. So I'm just going to flip it across my quadrants. And here's what it'll look like now. Alright. Ooh, gosh. And remember, the whole point of asymptotes is that it's going to get infinitely close to those lines, but it's not going to cross it. Now, just so you see this, I've seen a lot of people graph these things, and they just put a point on there, and they're like, yeah, it does something like that. Some kind of weird crab claw looking thing. No. Be precise with it. It approaches the asymptotes. It gets close to the asymptotes. So you can get close to that asymptote, but don't touch. Alright, domain is x cannot be 3. Range is y cannot be 2. Because you can't touch your asymptotes. X equals 3 for a vertical asymptote, and y equals 2 for a horizontal asymptote. Alright, so let's come up with a function for a couple of these here. Number 3. Alright, so again, I start with 1 over x, right? And now I'm transforming that. So I'm going left 4 and down 2. Okay, so I'm going left 4, down 2, and I'm starting in the positive quadrant, so I'll leave that as a positive. That's all there is to it. These over here, looks like I'm not moving up or down at all. My horizontal asymptote is still 0, but I am moving left 6. And then notice my graph is negative because I'm up here in this, you can kind of call it like the second quadrant, right? So my graph is negative. I'll need a negative out there. So it's not terrible. Alright, so let's get back to why we needed long division in the first place. Proper rational form is when the degree of the numerator is less than the degree of the denominator. So I need a smaller degree on top and a bigger degree on bottom. Okay? And I'm going to use long division to write each rational expression, all these down here, in proper rational form. So here's what they're talking about. See how this is x squared on top? I call that top heavy because the bottom is just x. So this is top heavy. Top heavy is no fun. We need it bottom heavy. So I'm going to set this thing up. X plus 3. I've got 2x squared, 0x, and 0. Fill in all my blanks. And I'm going to do these very, very quickly just for the sake of time. X goes into 2x squared. We're missing the 2x. 2x squared and 6x. Subtract both. Negative 6x plus 0. I'm missing a negative 6. And then minus 18. Change the signs. I end up with 18. Now the way that we would write this then is 2x minus 6 and this remainder of 18 plus 18 over x plus 3. That's how you write remainders. Plus your leftovers divided by what you're dividing by. And see, now it's bottom heavy. I've got a bigger degree on bottom than I do on top. This is x to the 0 power. This is x to the first power. Now it's bottom heavy, and it's all good. Number 6. So I've got 3x plus 5 being divided by 6 minus x. Now, I don't like the way that 6 minus x is written. I'm going to change that to a negative x plus 6 just to make everything all good. Negative x and 3x, what am I missing? I'm missing a negative 3 because negative 3 times negative x is 3x. Negative 3 and 6 is negative 18. Change the signs. 5 plus 18 is 23. So it's at positive 23. It's going to be plus 23 over negative x plus 6. Negative 3 plus 23 over negative x plus 6. Okay. Down here, number 7, I've got x to the cube on top, x to the 4th on bottom. So I'm already bottom heavy, so I'm done. Yay! Oh, happy day! It's already bottom heavy. We say the degree of the numerator is already smaller than the degree of the denominator. Remember, degree is your leading exponent there. So I'm done. Number 8. X to the 4th on top and x squared on bottom. Ooh. Okay, let's see what happens. I've got x to the 4th plus 0x cubed plus 2x squared plus 0x plus 1. and I'm dividing by x squared minus x plus 1. So x squared into x to the fourth, I'm missing x squared. We've got x to the fourth, negative x cubed, positive 1x squared. Change your signs everywhere. Wave them like you just don't care. I've got x cubed plus x squared plus 0x. Bring down that 0x. X squared into x cubed. I'm missing a positive x. X cubed, negative x squared, and plus x. Change the signs everywhere. I've got 2x squared minus x plus 1. And I'm missing a 2. So 2x squared minus 2x plus 2. Change signs everywhere. And I have got x minus 1. So I'm going to rewrite this as x squared, this guy up here, plus x plus 2, and then plus x minus 1 over x squared minus x plus 1. And that's all she wrote. Notice it's bottom heavy now. I've got a bigger denominator on the bottom. And technically this is the proper way to write things. Until you get to calculus, and then you get to throw all the rules at the wall and say, goodbye, rules.